This is why you need a thermometer. Because guessing is it hot just doesn't cut it in science. Let's see how one tool changed everything. Long ago, Galileo built glass tubes that danced with heat, but the journey didn't stop there. Mercury thermometers brought precision, watching silver rise as temperatures soared. Fast-forward digital sensors and infrared tech now measure heat without even touching. Each leap turned feeling into numbers, and numbers into data. Science went from its warm to its 37.0 degrees. The thermometer didn't just measure heat, it sparked revolutions in medicine, physics, and chemistry. So next time you check the weather or your fever, remember you're holding centuries of innovation in your hand. Follow us on For Science Salah Lotfy channel until the end of the episode.
Welcome to For Science Salah Lotfy channel, where global scientific research becomes clear and accessible.
هنا نحول الأبحاث العلمية العالمية إلى معرفة مبسطة مترجمة لك بلغتك.
Ici, la science est expliquée et traduite pour tous.
Ciencia clara, accesible y disponible en varios idiomas.
Wissenschaft, verständlich und mehrsprachig für jeden.
قناة For Science Salah Lotfy channel. العلم للجميع وبجميع اللغات. تابعنا لاكتشاف المزيد.
Before science could measure heat, humans already felt it. Warmth from the sun, cold winter nights, the heat of fire, and of the human body. For thousands of years, heat was experienced, but not understood. On For Science Salah Lotfy channel, we continue our series on the history of scientific measurement instruments, and today we explore one of the most fascinating questions in science. Why was heat a mystery before it was measured? How did heat become temperature? Unlike weight or length, heat could not be held, could not be compared directly, and could not be separated from human sensation. One person's warm was another person's hot. This made heat a scientific problem. In daily life, we talk about feeling hot or cold. In science, we talk about temperature, a measurable physical quantity. But you know, reaching that idea took centuries. Why did temperature measurement appear later than the balance or the ruler? Well, because heat does not reveal itself directly. It only shows its presence through change, expansion, contraction, movement. Before thermometers, there was no reliable way to compare heat between places, between objects, or between moments in time. Science could describe heat, but it could not quantify it. And honestly, without measurement, there can be no experimental science. This is why the invention of the thermometer was not just a technical achievement, it was a conceptual breakthrough. It marked the moment when heat stopped being a sensation and became a number. In the next part of this episode, we will meet the first device that attempted to do just that. Galileo's thermometer, and see how a simple idea began the long journey from feeling heat to measuring temperature. Let's continue.
After Galileo tried to capture heat, science hit a wall. How do I actually temperature and not just feel it? The answer was risky: mercury. This silvery liquid did something incredible. It expanded the same way every single time. No weird surprises, no guessing games. For the first time, temperature became more than just hot or cold. It became a number. Mercury thermometers gave science a way to compare notes, not just across towns, but across the globe. Suddenly, I could say exactly how hot water was when it froze or boiled. Two simple points, freezing and boiling, and between them, everything clicked into place. But there was a catch. Mercury is toxic. Glass breaks. And to get a reading, I had to wait, sometimes way too long. Science needed something faster, safer, and more precise. That's where electronics came in. Digital thermometers ditched the liquid. Now, temperature changed electrical resistance. The thermometer turned that into a signal, and just like that, a number popped up on the screen. Fast. But what if I couldn't touch what I was measuring? Enter infrared thermometers. They don't need to touch. They read the heat an object gives off, like listening to its thermal voice. From liquid expansion, to resistance, to invisible radiation, the thermometer is really the story of science outsmarting its own limits. But that brings me to the big question. What even temperature, really? And how did we decide what 0 or 100 should mean? That's where the next part of this journey begins. Before numbers, before scales, there was only sensation. Heat was something I felt, never defined, never agreed upon. Warmth and cold were personal, secret languages, changing from one person to another. But that wasn't enough for science. If I wanted to truly understand the world, I couldn't trust just my skin. I needed to measure, to compare, to move beyond feelings. And the key? It turned out to be a surprisingly simple idea: thermal expansion. When matter heats up, its particles move faster. They need more space. So, the material expands. But here's the catch. Solids expand so little I can barely notice. Gases, on the other hand, expand wildly, unpredictably. Impossible to control. So what did science do? I turned to liquids. Liquids expand more than solids, but less than gases, and they do it smoothly, predictably, in a way I can actually see. But expansion alone isn't enough. If I just pour some liquid on a table, it's chaos. No measurement, no meaning. I needed a guide, a container, something stable. Enter glass. Transparent, stable, nearly immune to temperature changes, glass was the perfect partner. I could shape it into a narrow tube, and now, even the tiniest change in heat made the liquid creep higher or lower. For the first time, heat left a visible trace. But a trace is just a start. Observation is not measurement. I needed a way to compare. How high is high? How low is low? That's when the idea of a scale changed the game. I marked the glass with lines, each one meaning a fixed step. Now, motion meant something. Now, I could repeat it. I could share it. Temperature was no longer just hotter or colder. It became a position on a scale, a language anyone, anywhere could use. This changed everything. Heat became measurable. Measurement became universal. Science finally had a common tongue. From sensation to expansion, from expansion to scale, the thermometer evolved from a mere observer to a true measuring tool. And once I could measure heat, a deeper question emerged. Who decides what the scale should be? How does the whole world agree? That question, how we define temperature standards, that's where the story goes next.
Imagine a single silvery liquid, shimmering mysteriously in a glass tube, changing the course of science forever. It might surprise you, but mercury, yes, that quick-moving, reflective metal, sparked a revolution that transformed how we understand the world around us. Before mercury thermometers, temperature was just a vague sensation. Something you felt on your skin, not something you could measure or compare. Mercury made temperature measurable. Not just a feeling, but a number you could trust. Think about it. For centuries, people judged heat by touch or guesswork. Was it warm, hot, or freezing? It was all totally subjective, and there was no way to agree on what hot really meant. Enter Daniel Gabriel Fahrenheit, a visionary who realized that mercury, with its unique ability to stay liquid over a wide range of temperatures and expand evenly, could turn the mystery of heat into something you could actually measure. He crafted the first reliable mercury thermometer, forever changing science. Suddenly, temperature could be recorded, compared, and replicated anywhere in the world. Scientists from different countries could finally speak the same language of measurement, making discoveries more accurate and experiments more reliable. Fahrenheit's scale set the stage for a new era, and soon Celsius followed, giving us the temperature scales we still use today. These inventions made it possible to standardize science across continents. The mercury thermometer wasn't just a clever gadget. It was the key that unlocked the secrets of thermodynamics, powering groundbreaking experiments and discoveries in physics, chemistry, and beyond. It became a symbol of scientific precision, turning the invisible sensation of warmth into a concrete, reliable fact, one that could be shared, studied, and built upon. The journey of measuring temperature is still evolving. Want to see where science goes next? Subscribe and join the adventure as we explore the future of measurement.
Despite its central role in shaping modern thermometry, the mercury thermometer was never a perfect instrument. Its success revealed its limitations, and those limitations gradually became impossible to ignore. The first challenge was toxicity. Mercury is a hazardous substance. A single broken thermometer could contaminate a laboratory, turning a scientific tool into a health risk. From this moment on, precision alone was no longer enough. Safety became part of scientific design. Then came the issue of response time. Mercury reacts slowly to temperature changes. In experiments where conditions change rapidly, the thermometer often recorded what had already passed, not what was happening in real time. There were also physical limits. At very low temperatures, mercury freezes, and at high temperatures, it approaches boiling. These boundaries restricted the environments in which the thermometer could operate reliably. Even the surrounding environment mattered. Changes in pressure, altitude, and external conditions could subtly influence readings, reminding scientists that every measurement is affected by its context. But in science, limitations are never the end. They are signals, pointing toward the next stage of development. Each weakness raised new questions. Can temperature be measured without toxic materials? Can it be measured faster? Can it be measured beyond the limits of liquid expansion? These questions transformed problems into drivers of innovation. They pushed thermometry beyond glass and liquid, toward electronic sensors, digital systems, and non-contact methods. The mercury thermometer did not fail science. It played its role perfectly, by showing scientists what needed to change next. And from its limitations, the future of temperature measurement was born.
The next leap in temperature measurement did not come from glass or liquid. It came from electronics. This was the moment when heat stopped being observed visually and started being translated. At the heart of the digital thermometer are thermal sensors. Thermistors change their electrical resistance with temperature. Thermocouples generate a small voltage when two different metals experience heat. In both cases, temperature is no longer something we watch rise. It is something we detect electrically. Here, heat is converted into an electrical signal. That signal is amplified, processed, and interpreted by a circuit. What once took seconds or minutes now happens almost instantly. Speed became a defining advantage. Rapid changes could finally be captured in real time. And with electronics came a new language: numbers on a screen. No parallax error, no subjective reading, no interpretation of a liquid column. The measurement became direct, clear, and repeatable. This was a fundamental shift in scientific thinking. Temperature was no longer something we see. It became something we convert. Heat was transformed into data. And with that transformation, thermometry entered the digital age, faster, safer, and more precise than ever before.
The evolution of thermometry reaches a point where touch is no longer required. This is the era of the infrared thermometer. Every object around us emits thermal radiation. Not visible light, but infrared energy, radiation that carries information about temperature. Even in complete darkness, this emission never stops. Infrared thermometers are built on this simple truth. To measure temperature, you no longer need to make contact. You only need to detect the radiation leaving the surface. A sensor captures this invisible energy. Electronics translate it into a temperature value. In just a fraction of a second, heat is measured from a distance. This technology honestly changed everything. In medicine, it allows temperature measurement without touching the patient, reducing risk and, well, discomfort. In industry, it makes it possible to monitor moving, fragile, or extremely hot objects. Situations where contact is just impossible. But, this power comes with a crucial distinction. Infrared thermometers measure surface temperature, not internal body temperature. Understanding this difference is, honestly, essential for correct interpretation. The infrared thermometer reminds us of a profound scientific fact. Every object emits radiation. Heat does not need to be seen. It only needs to be detected. With infrared thermometry, science learned to read the invisible language of energy, extending our ability to measure temperature beyond touch, beyond light, and into the realm of radiation itself.
If you don't trust your weather app but still rely on your thermometer, then it's time to check what's really going on. Imagine thermometers as storytellers, each one with its own version of the truth. We often take their readings for granted, but have you ever wondered how these devices know what temperature it really is? The answer is more complex than you might think. Each thermometer gives you a number, but not every story is true. The secret behind their reliability? Calibration. Without it, even the most advanced thermometer can lead you astray, giving you numbers that are more fiction than fact. No thermometer is born accurate. Each has to be taught what hot and cold really mean, by comparing it to trusted reference points, like the freezing and boiling points of water. This process is called calibration, and it's the foundation of every trustworthy temperature reading. Calibration isn't just a one-time event. Over time, thermometers can drift, losing their accuracy as their components age or as they're exposed to different environments. That's why regular recalibration is essential, especially in scientific and industrial settings. Think of calibration like setting your watch to the official world clock. Just as you wouldn't want your watch to be a few minutes off, you don't want your thermometer to be a few degrees off either. Without calibration, your sense of time, or temperature, drifts. But wait, there's more. Even a calibrated thermometer has other challenges to face. Sensitivity is how much a thermometer jumps when temperature shifts. Some thermometers react instantly, while others take their time to catch up. This responsiveness can be crucial, especially in situations where temperatures change rapidly. Accuracy, on the other hand, is how close the thermometer lands to the true value. It's not enough to be quick, you have to be right too. You can have a thermometer that's quick to react, but still gets it wrong. That's why both sensitivity and accuracy matter. In science, we demand both. Reliable measurements are the backbone of experiments, weather forecasts, and even the food we eat. Calibration is where accuracy is born, and precision is perfected. It's a meticulous process, often involving specialized equipment and expert hands. So, next time you read a temperature, remember, behind every number is a careful process, a scientific anchor, and a promise that you're not being fooled. The next time you check the weather or measure a fever, you're seeing the result of hidden science working hard to keep you informed and safe.
From Galileo's glass spheres to infrared sensors and digital displays, thermometers have changed shape, material, and technology. Yet, something essential never changed. The core principle remains the same. Heat is linked to a physical change. Whether it is the expansion of a liquid, a change in electrical resistance, or the emission of radiation, temperature is always revealed through transformation. Only the method evolved. Glass became silicon. Liquid columns became electrical signals. Contact gave way to distance, and still, the thermometer remains indispensable. Because, without measuring temperature, there is no chemistry, no physics, no biology, and honestly, no understanding of natural processes. The thermometer is not just a tool. It's really a bridge between sensation and knowledge, between heat and energy, and even between observation and explanation. When science learned how to measure temperature, it actually began to understand energy itself. This journey through thermometry is part of a larger story. The story of how scientific instruments turned the invisible into the measurable. In the next episode of this series, we will explore another fundamental instrument, the barometer, and how measuring pressure opened a new window into our atmosphere and our world. So, stay curious.